So combustion. We keep coming back to this concept of combustion. One, it's running through your textbook. Two, they're good reactions for people to understand. Three, when we start work on chapter 5, there's a series of different types of reactions. You just have to understand how they work, and combustion is one of them. Combustion occurs when a hydrocarbon is a compound that contains only carbon and hydrogen atoms. So a hydrocarbon, hydro again meaning hydrogen, carbon meaning carbon, or a compound containing only carbons, hydrogens, and oxygens undergoes complete combustion in oxygen, in the presence of oxygen. The products formed will be CO2 and water. When I say complete combustion, there's a very specific reason I am using the word complete combustion, because complete combustion results in products that are CO2 and water. Incomplete combustion is when you have a reaction going with an insufficient amount of oxygen present, and then we actually produce carbon monoxide and water, which is not what we want, because we as humans we can easily breathe out carbon dioxide. Unfortunately, our hemoglobin, which is what carries the oxygen molecules throughout our body, when it finds carbon monoxide, it actually bonds better. The iron within the hemoglobin bonds to carbon monoxide better than oxygen, than the diatomic oxygen. It's a slightly smaller molecule and it fits in there a little bit better. That's not a good thing, because carbon monoxide isn't going to oxygenate our bodies and we're not going to survive that. Most often what actually happens is a mixture of the two. We just want to limit the amount of carbon monoxide being produced. In the real world, 2 ways we do this. 1, catalytic converters. They are there to help add oxygen to the system while it's burning, while your gasoline is burning in your engine. The other way we try to combat this in our real world is, if you've ever filled your tank up with gas, it will tell you on the gas pump that it has a certain percentage of ethanol in it. Ethanol is CH3, CH2, OH. It is a carbon hydrogen containing compound. It is also known as an alcohol. It's also what people drink. So if you think about alcohol drinking, this is the alcohol that you can drink. This is ethanol. Other alcohols you do not drink. This one you do, or if you drink. But this is put into gasoline. And the whole reason behind that is because we can increase the oxygen content in the gasoline so that when it's burning, there's more oxygen present outside of just what's naturally around and available in the atmosphere. So it's more likely to undergo complete combustion instead of incomplete combustion, therefore just making it safer for us. You are, however, responsible for knowing how to balance these. And specifically, you need to know how to balance complete combustion reactions. I'm not going to make you balance incomplete combustion reactions, but I tell you about them because I feel as an informed human being, you need to understand the point of putting ethanol in your gasoline, the point of what's actually happening when these are burning in your engines or other places. So, 2 examples. Number 1, write the complete balanced equation for the complete combustion of ethane, C2H6, and oxygen. Also, I love this photo here. This is very much what my high school or my college classroom looked like for chemistry. And we did demos like this kind of regularly. Students did them, and it was really, really fun. We do them for schools and stuff like that. We did have people that, we had supervision and stuff like that. But we do huge frames like this. It was a lot of fun to do these demos. So I really like this picture. So you guys get to look at it too. Anyway, let's go ahead and look at the complete combustion of ethane, C2H6, in the presence of oxygen. So I've got C2H6. This is going to be burnt in the presence of oxygen, and it's going to form CO2 and water. Put our phases in. Now, I know you don't know this from the question, but C2H6 is a gas. Ethane is a gas. Oxygen, you need to know is a gas. Carbon dioxide, you should know is a gas. And water, depending on the temperature you're at, can form a gas or a liquid. It can form water vapor or a liquid. But when I look here, I'm going to look and see, okay, I've got carbons, hydrogens, and oxygens on each side of my reaction. I'm going to write the product side over here. To start off, I have 2 carbons, 6 hydrogens, and 2 oxygens. On my product side, I've got 1 carbon, 2 plus 1, so 2 oxygens there, 1 in the water. So overall 3 oxygens present. So I'm not going to be able to, I normally would write 2 plus 1, but I'm not going to be able to fit it over here. And then 2 hydrogens present. First thing I see is that my hydrogens are not balanced. My carbons are not balanced. I need to go ahead and balance those first. So I'm going to go ahead and put a 2 in front of my CO2 here. That balances out my carbons. But now I have a different number of oxygens. I have 4 plus 1. I have 5 oxygens now. I also need to balance out my hydrogens. I have 6 on my reactant side and 2 on my product. So I'm going to put a 3 in front of there to balance out my hydrogens. Now I have 6 hydrogens on each side, but now I have 4 plus 3, I have 7 oxygens. Now, I can go back and forth like this all day, but what I'm going to tell you is that you're probably going to get frustrated and mess it up, frustrated and give up, or possibly lock into the right answer. The easiest way to answer this, when you've got this even, odd combination with a diatomic, this will happen with diatomics, and it is painful. What you need to do is give yourself a fraction. Write 7/2 O2 over here. 7/2 of O2 is 7 oxygens. So if I, because this is the 7/2 here is the same as saying 3.5 times O2. That's giving me 7 oxygens on each side. If I do that, I now have 7 oxygens on each side. I cannot leave this as a fraction, but this is the fastest way to get to the right answer. Okay? Now I've got the exact same number of elements on each side. Now I just need to get rid of the fraction. What I'm going to do is I'm going to multiply through the compound, the entire reactant side and product side. I'm going to multiply through by the value in the denominator. So I'm going to distribute this 2 through this entire compound. What do I mean by that? Well, let me show you what I mean by that. I'm going to say 2 C2H6 plus 7 O2, because 2 times 7/2 is 7. Four CO2 and 6 H2O. Now I want to go back through and just make sure that my answers are correct. When I look at carbon on my reactant side, I have 4 carbons. Hydrogen, I have 12 hydrogens. Oxygen, I have 14 oxygen. On my product side, 4 carbon, 12 hydrogen, and 8 plus 6, or 14 oxygen. It is balanced. When you are doing complete combustion and you're using a compound that is carbon and hydrogen only, sometimes carbon, hydrogen, oxygen, you also need to do fractions. But especially when you see this carbon-hydrogen combination, at least 50% of the time, you're going to want to deal with a fraction to make your life easier. Now, again, you don't have to. You can play this game back and forth, keep trying to balance them. But it is easiest if you, again, what we had 7 oxygens over there and 2 over there, or on the reactant side. So I just put the bigger number over the smaller number and put that as the coefficient on the side that had the smaller number. I then multiplied through the entire reaction by the denominator. It cleaned it all up for me, and I didn't have to play the games with it, and I was able to balance it very quickly. I highly recommend you practice. There's extra examples like this in the problems, the extra additional problems that I've worked at the end. The problems are in your PowerPoint, they're in your student notes, they're worked out in the video. I highly recommend you work some extra problems to get comfortable using these fractions. Okay, next example. When the balanced equation for the complete combustion of ethanol, CH3CH2OH, is written using the smallest whole number coefficients, what is the coefficient on oxygen? So I've got ethanol. Let's see, find a color you guys can actually see on here. I don't know if you'll be able to see. Okay. No, I'm trying to find a color that looks fun background, but not an easy background to see. CH3, I'm going to go back to green. CH3, CH2, OH, plus O2, and ethanol is a liquid. Oh, you can actually see the white on here. I apologize. I like the fun background, but I just want to make sure you guys can see it. CH3, CH2OH is a liquid, plus oxygen gas, giving me CO2 and water. So, carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Here I see I have two carbons. I've got one here and one here. You can write the ethanol formula the other way as well. You can write them all together. So you could write ethanol as C2H6O. It might be easier while you're balancing, so you don't do what I just did and miss the one carbon. Two carbons, let's see, 1, 2, 3, 4, 5, 6 hydrogens, 1, 2, 3 oxygens. On my product side, 1 carbon, 2 hydrogens, 3 oxygens. I need to balance my carbons first, so I'm going to go ahead and put a 2 in front of the CO2. This is going to give me 2, my CO2s. It's going to add 2 more oxygens to my compound here. So now I'm up to 5 oxygens. Next, I'm going to balance my hydrogens. Put a 3 in front of here. That gives me 6 hydrogens and 2 more oxygens. Now I'm up to 7 oxygens on that side. Clean that up a little bit over there. 2, 6, and 7. I need to get 7 oxygens on this side. Don't forget you have 1 oxygen here in your ethanol. Put a 3 here. This gives me 6 oxygens. This makes number 7. Now I've got 2 carbons on each side. I've got 6 hydrogens on each side, and I've got 7 oxygens on each side, and this reaction is completely balanced. Combustion reactions are easier to balance when you've got a carbon, hydrogen, oxygen containing compound because you've got oxygen in multiple sources. The mistakes students will make is they'll forget this oxygen right here. And so instead, they'll use fractions, forgetting that oxygen in the middle here, and mess it up. So if you need to rewrite it in a form like this, that's completely acceptable. The reason I write it like this is because in organic, we're going to write it like this. And that's how my mind sees it because I work with the organic kids so much that you're going to see it like that in organic, so I'm going to write it that way. You are welcome to rewrite this in this form if it helps you balance it this semester. But you do need to get comfortable seeing them in this form and recognizing the oxygen even within the formula like this. So make sure you practice more balancing of combustion reactions because it is important throughout this entire semester.